Okay, so today we will be discussing different topics. The first part is about the variable mass problems. So in variable mass problems, we will discuss about a control volume that loses mass, which you can see in this case that the rocket is moving, and during the motion it loses mass in term of the fuel. So the mass is changing during the motion here. Similarly, we can have a system uh, where the system will gain mass, as you can see in this figure here. That when the hook will moving in the upward direction, the mass of the chain is increasing. So this will comes in this category here. So we will discuss each of these topic in detail, and we will derive the equation of motion for it. So if we start the first part here, that is the control volume that loses mass. So in this case, we will consider a very simple sort of uh, figure here. So consider a device such as a rocket or balloon, uh, which at an instant of time has mass m and is moving forward with velocity v. So as you can see in this case here, so you have a balloon of mass m, and the velocity is toward the right. The velocity of the ejected mass at time t is me, and the velocity of this mass is ve. Now, at this same instant, the amount of mass me is expelled from the device with a mass flow velocity ve. Now, for the analysis, the control volume will include both the mass m of the device and the expelled mass me. So instead of the just the balloon, we will consider this whole control volume here, uh, which consists of the mass me and mass of the balloon here. Now what will happen that during the time dt, so after time dt, the it, its velocity is increased from v to v plus te. So the velocity of the balloon is increasing from v to v plus te, and since an amount of mass dme has been ejected and thereby gain in the exhaust, so what will happen is the if you want to draw the impulse momentum diagram for that specific case, so at time t, the balloon was at this position here. We can say that this is our time t, and the so before the so this was the mass of this uh, uh, fuel was me, and the mass of the balloon was m, and its velocity is v. So if its velocity is v, so the momentum of this will be m v. And if the velocity of uh, this fuel is me, and its velocity is ve, which is in this direction, so its momentum will be meve. And of course we are drawing the impulse and momentum diagram here. So what will happen is that uh, you will have the initial momentum plus impulse. So impulse in this case will be, so there will be some forces applied to the control volume, some external forces. So we will call these forces is summation of all the forces uh, on the control volume, and we will multiply this with the dt. So dt means it's uh, the force multiplied with time. So this is the impulse, and this is, we know that it is time dt, so during time dt, and this will equal to the final momentum of the system here. So the final momentum of the system is this case, the mass is expelled from the balloon here, So it become m minus dme. So the amount of mass which expelled from the balloon in time dt. So this is time t plus dt here, and the mass of the air or balloon is now me plus dme. So the dme comes from the balloon and added to the mass of this air or fuel here. And in this case now, because uh, the velocity of this device become v plus dv, and this dv is the change in velocity or increase in velocity. Initial velocity, which was v, now become v plus dv, and the mass become m minus dme. So the momentum of this system will become m minus dme into velocity, which is v plus dv, and momentum of this gases or fuel will become me, and it's obviously in this direction. So me plus dme, and there will be no change in the velocity of the expelled gases. So the velocity is again ve here. So this is the impulse and momentum diagram. So what we have the initial momentum of the system, which is the momentum of the device mv, and minus meve because it's in this direction. And then at time dt, a force is acting on the control volume here, and we will just find out its impulse. We will multiply with the time dt, and it will be equal to the final momentum. So if the final momentum is again a mass is ejecting from the device here, dme, which will aid to this mass here. So, and because the velocity of this is again ve, so this will become me plus dme, which is this mass into ve, and the velocity of the balloon or rocket is increasing. So it will become v plus dv, and the momentum of this device will become m minus dme, which is the mass times velocity now. Okay, so after doing this, again you can see the same diagram here. Now the increase in forward velocity, however, does not change the velocity ve. As we said earlier, the velocity ve remain the same. As seen by the fixed observer, since the mass moves with a constant velocity once it has been ejected. Now this impulse, which we discussed earlier, the impulse or created by this forces on the control volume, which represent the resultant of all the external forces such as drag or weight that act on the control volume in the direction of motion. Now this force resultant does not include the force which caused the control volume to move forward. So in this case, this forces on the control volume only represent the forces which are external. It's not include the thrust that you may be expecting here. Since this force called the thrust is internal to the control volume, so thrust is internal, and that is the thrust acts with equal magnitude but opposite in direction on the mass m of the device in the expelled exhaust gas me. So you will see this in a minute, that how we will include thrust in this whole diagram here. So now if you apply the principle of impulse and momentum to the control volume, so in this case, we are now trying to derive the equation for this specific case. So we will need to, we already have the diagram here, but now we need to write this in term of the equation. So the impulse momentum equation is that you have the g1 plus impulse, so t1 to t2, uh, summation of all the forces dt equal to g2, So in this case, our G1 is the belong to this part here. So in this case, the whole momentum will consist of this MV and this MEVE. But obviously, if we take this is our positive direction, so MV minus MEVE is uh, before the applied force, and then you apply some force on the system for time dt. So it will become like this. And then on the right hand side, we have the momentum of the device, which is this part, and momentum of the gases, which is this part here. So again, this is positive and this is negative. So you can say that m minus m dme v plus dv, and then minus me plus dme and ve, which is this part here. We have this equation for the principal impulse and momentum when we apply to this figure here. So now we can simplify this equation. If you just simplify this equation, so it will become dv dt will become equal to minus v dme plus m dv minus dme uh, dv and minus ve dme. So it is just, if you multiply these terms together, you will end up with this equation here. Now, if you look at this equation here, in this case, uh, even we can ignore this term here. So we can say that this term is equal to 0 because it's the multiplication of two very small terms, and the reason is because so one is dme and one is dv, so both are small terms. So if you multiply two small terms, you will get uh, a very small term. So we can ignore this term. Obviously, this will introduce some error into the equation, but it's fine in this particular time. We have this equation here now. So if we drop this term, so what we will have, we will just end up with this equation. So fcv dt we just move dt to this side here, so you will get minus v plus ve and dme divided by dt. So you will get this equation here. So on the left hand side, we have summation of all the forces on the control volume. On the right hand side, we have m dv by dt, and this dt is just, you move this dt to the other side, and then you have minus v plus ve and dme divided by dt here. Now this v plus ve is again, you can visualize this. So the velocity of the device is seen by an observer moving with a particle of the ejected mass is VDE, which is V plus VE. So if an observer is sitting here, so if an observer is sitting here, and he or she want to observe the motion of the device, so it will be just V plus VE. So this is just a relative velocity. So VDE, this means that it's the velocity of the device relative to the expelled gases, or the other way around, it can be the velocity of the expelled gases with respect to the device. And so the final result can be written as this. So finally, then we can write the summation of all the forces on the control volume. That will become equal to m dv by dt and minus. So then we just replace v plus ve by this relative velocity, and then you have the dme divided by dt here. So this is again a very important equation that you will be using in the numerical example for solving problems. So in this case, now we will explain each and every term in this equation. So what these different term means. So if you consider this rocket here, so the drag force is in this direction, which is opposite to the motion, to the direction of motion. The velocity is in this direction. It's moving in the upward direction. The weight is in the downward direction here. Uh, so in this case, the term, this term here, which is dme divided by dt, it's represent the rate at which the mass is being ejected. So this means that the rate of mass with respect to time of the me means the mass of the expelled gases. And if you consider this rocket here, which has a weight w and is moving upward against an atmospheric drag fd. Now the control volume to be considered consists of the mass of the rocket and the mass of the ejected gases me. So in this case, if you apply this this equation here, if you apply this equation here, so on the left hand side you have summation of all the forces on the control volume, which is not internal. So in this case, we know that it is minus fd, because it's again we are taking this as our positive direction. So minus fd is the drag force, minus w is the weight of the rocket. On the right hand side, we have m, so m is again w by g, and dv by dt is just acceleration, so dv by dt. And then you have this vd with respect to e, and you have dme divided by dt here. So for this rocket, you can write the equation of motion in this form here. Now here again, this term here is again a very important point that you need to understand here. So now, because in this equation you have the force, which is fd, again w is a force, and again this is just ma, because this is m and this is a, so ma is again force. So this means that this term should also be force. And what this term is, the last term of this equation represent the thrust. So this is our thrust actually, which the engine exhaust exert on the rocket. So if we just recognize that dv by dt is equal to a, we can therefore write that uh, if we just replace this by t, so and if we just move this to the right hand side, the left hand side, it will become t minus fd minus w equal to ma. So and if you look at this equation here, it is nothing but just the Newton's second law. So this is summation of all the forces, which is summation of all the forces, which is t, the thrust, the fd, which is the drag force, and the uh, weight equal to ma. So this is just the uh, uh, just this Newton's second law. So if a free body diagram of the rocket is drawn, it becomes obvious that this equation represents an application of the Newton's second law, which is summation of all the forces equal to ma for the rocket. So this means that if this equation is nothing but just the Newton's second law, and again this is important to know that this term is the thrust, because it's just the if you just put this velocity inside the d, so it will become the rate of change of momentum of the expelled gases, which is again the force, and that force is what we call is the thrust here. Okay, so this was the first case, that is the system loses mass. But the other situation can be is that the system can gain mass, as you can see in these figures here. So in this case, if you consider this just imaginary device, that this balloon is moving in this direction and it's now collecting mass rather than ejecting mass, as was in the previous case. The device has a mass m, the initial mass was m, and move forward with the velocity v. So the velocity v, which is in the toward the right. At this instant, the device is collecting a particle stream of mass mi. Now this mass which is here is going inside the device here. Now the flow velocity vi of this injected mass is constant and independent of the velocity v. And in this case, if the v is greater than vi, so this means that this uh, mass will go inside the balloon. Now the control volume to be considered here include both the mass of the device and the mass of the injected particles. Now we can draw the similar to the previous case. We can again draw the impulse momentum diagram, as you can see in this case here. So in this case, along with increasing in mass dmi gained by the device, there is an assumed increase in velocity dv during the time interval dt, and this increase is caused by the impulse created by this forces which may be acting on the device here. So in this case, as you can see, the initial mass of the device was m, so its momentum is mv because the velocity is v in this direction. The initial mass of this gases is mi, and the velocity was vi, so the momentum will be mi vi. And now there will be some forces on this device here, so the impulse of that forces will be forces times dt. And on the right hand side, we have the final momentum. So in the final case, what will happen that some of the mass will go inside the device, so the mass of the device will increase from m to m plus dmi, and mass of the outside gases will decrease because this mass is now inside the device, so it will become mi minus dmi. So if we know the mass of this device here, and the velocity of the device is also increasing from v to v plus dv, and this change in velocity may be due to some forces which are acting on this device here. So the final momentum will be m plus dmi plus into v plus dv, and the mass of the expelled gases is of the gas here is now mi plus dmi. So if you just multiply this with vi, because the velocity of these gases will not change, it will remain constant. It will become mi minus dmi. Okay, so now if you want to uh, draw the write the equation of motion for this, so the force summation does not include the retarding force of the injected mass acting on the device. So you may think that why we do not include the force which is the retarding force of the mass which is going inside the device, because that force is internal force like the thrust force, and we will not include this in this summation of all the forces cv, but that will comes at the end. So if we now apply the principle of impulse and momentum to the control volume here, so similar to the previous case, we will consider that this is our positive direction. So again, for before the application of the force, the initial momentum is mv for the device, and plus mivi for the gases, and then you apply this forces on this device here, and then the final momentum will be this is for the device, so m plus dmi, and the velocity will become v plus dv. And then for the gases, the new mass is m minus dmi, and the velocity is vi. So we end up with this equation here. Now, if you just simplify this equation like you did in the previous case, so what you will get, you will end up with this equation: mcv m dv by dt and plus v minus vi and dmi divided by dt. Okay, now in this case, similar to the previous case, now this velocity, which is v minus vi, is again a relative velocity. This is a relative velocity since the velocity of the device is seen by the observer moving with the particle of the injected mass is vdi. So we can represent this by vdi, which is v minus vi, which is the relative velocity of the gases with respect to the device here, which can be balloon or rocket. So the final result can be written as like this. So summation of all the forces. So if we just replace this v minus vi by vdi, which is the relative velocity of the device with respect to I. So this term means the velocity of the device with respect to the injected gases, and then we will have dmi divided by dt here. So this is the final equation that you will be using in solving numerical examples. Okay, so now in this case, because we have this equation here now, if control volume is equal to m dv by dt and plus vdi, and then you have dmi divided by dt. So again, this dmi by dt is the rate of mass injected into the device, and the last term in this equation represent the magnitude of force r, which the injected mass exert on the device. So this thing is including this thing here is what we call is this is our is the retarding force, and uh, this retarding force which you can represent by r here. So if you just try to write this the r and just move the r to the other side, so the equation will become this equation here. So again, summation of all the forces minus r equal to ma. And in this case, we know that this is the application of the Newton's second law. It's nothing, just Newton's second law. Okay, so just to summarize the this part of the lecture today, we discussed a variable mass problem, and there were two situations. The first one was that the control volume that loses mass, as you can see in this case here, so which can be a balloon or rocket. So this was the impulse momentum diagram. So the initial case, and then there were some forces on the system. You will try to calculate its impulse, and then this is the final momentum. So if you write the equation of motion for this case and you simplify the equation of motion, you will end up with this equation. So summation of all the forces on the control volume equal to mass times velocity of the device minus the relative velocity of the device with respect to the ejected gases, and then this is dme divided by dt, uh, which is the rate of uh, rate of the rate at which the gases are ejecting from the device. And finally, then we discuss a system or a control volume that gain masses, which you can see in this case here. And in this case, again, we assume this sort of situation here, that a balloon is moving and collecting some gases. So again, this will be the impulse momentum diagram. So initial momentum plus impulse equal to the final momentum. And if we write the equation of motion for this, then we can simplify the equation, and we will end up with this equation here. And again, you can see here that we have the forces on the control volume, which is equal to m dv by dt, so which is the mass times acceleration of the device, and plus the relative velocity of the device with respect to the injected gases. And then again, dmi divided by dt is the rate of change of the gas injected into the device here.